Welcome! This is Year 8 Competence-Based Middle Years Program Level 3 Sciences. Workshop number 3. This session is still part of Unit 1. We will go on revising the basics, and in particular, we will continue with the Uniformly Accelerated Rectilinear Motion, UARM. We will review one of the problems we did last year. Example 1I. A squirrel is eating a nut on top of a tree. The nut falls onto the floor with acceleration caused by gravity, which is 9.8 meters per second squared. If the squirrel was 4.9 meters high, solve A. The speed the nut will have 1 second after it fell. B. The equation of the position of the nut. C. The time it takes to hit the ground. In addition to that, represent D, the speed of the nut versus time, and E, its position versus time. So let's start drawing a scheme. We have a squirrel on top of the tree, 4.9 meters above the ground. Given that the nut is initially at rest because the squirrel is eating the nut, we will take that point as 0. And given that it will only move downwards, we will take positive downwards. Now, if we start at 0 and positive is downwards, any point beneath the origin is positive. And given that the squirrel was at 4.9 meters from the ground will be plus 4.9 meters. Let's now focus on the first question. The speed in terms of time in a uniformly accelerated rectilinear motion is given by v equals v0 plus acceleration times time. Therefore, the speed it will have 1 second after it fell will be given by v equals 0, which is the initial speed, times the acceleration, 9.8 meters per second squared, times the time, which is 1 second. That gives us 9.8 meters per second. The position is given by the expression r, position, equals r0, initial position, plus v0, initial speed, times time, plus a half of the acceleration times the time squared. In our case, the origin of coordinates is the initial position because it starts from 0. The initial speed is 0 because the squirrel was eating the nut, so the nut was at rest. And the acceleration is 9.8 meters per second squared in the sense we have chosen as positive, therefore plus 9.8. That is 0 plus 0 times time plus a half of 9.8 times time squared, which is 4.9 times time squared meters with t in seconds. Let's now solve the remaining parts of the problem. See the time it takes to hit the ground. Hitting the ground, remember, is reaching position 4.9, which is 4.9 meters beneath the origin of coordinates with positive sign being downwards. We know the expression of position in terms of time because we just found it. So we replace the final position, which is 4.9, at its right place. Therefore, we obtain 4.9 equals 4.9 times t squared. We simplify 4.9, we obtain t squared equals 1. That means t equals 1 second. Actually, to be precise, what Dr. Mathematics is telling us is t equals plus minus 1 second. Does that make sense? Let's consider for a moment, what we are asking Dr. Mathematics. The question we have posed in this equation is, what are the values of time for which the moving body finds itself at position 4.9 if it was at position 0 and at rest, position 0, 0, because it was at the origin of coordinates, and at rest because the knot was not moving, for time equals 0. Remember, time equals 0 when we start counting. The knot is at rest, it's when it starts falling, and it is at the origin of coordinates, position 0. Therefore, 4.9 equals 4.9 times t squared. And Dr. Mathematics is telling us, if the knot is at 0 up here and at rest because it's not moving yet, when time equals 0, the values for the knot, the moving body, to be at 4.9 are -1 second and +1 second. Does that make sense? Yes, it does make sense, because Dr. Mathematics does not care it is a knot, and it does not care it was in the hands of a squirrel. Dr. Mathematics is saying that a moving body, whichever, that is at 0 and at rest when the time equals 0 and with a constant acceleration of 9.8 meters per second downwards, will be at 4.9 at -1 second and at +1 second. That would mean that if the moving body had come from the bottom of our scale, wherever it is, going up, it would have passed the height 4.9 1 second before stopping at 0, and then it would go back again through 4.9 1 second after having stopped. That is the sense, that is the meaning of those minus and plus 1 second. Let's now focus on the representations. We need to represent the speed of the knot versus time first, and its position versus time. We know that the speed of the knot is given by v equal 9.8 t meters per second with t in seconds. We build a table of values for the different values of time, and we obtain the different values of speed, replacing those values of time in that equation. When we represent speed versus time, we obtain a straight line, obviously, because the speed is changing at a constant rate. Therefore, the slope of the curve is constant and we have a straight line. When we want to represent the position versus time, remember that position is given by 4.9 times time squared in meters with t in seconds. If we build the table with the values for the different values of time, we obtain the different positions. And when we represent those positions, what we obtain is half a parabola, because the position depends on the squared of the value of time. Therefore, it is half a parabola. This is it for now in life and in sciences. As always, enjoy.